All right. All right. So let's start with the next section on DC to DC converters, which is boost converters in part 5C. And in this particular section on boost converter, we'll be discussing the basics of boost converter with mathematical derivations. And then later on, we'll be discussing about the practical aspects of buck and boost combined together. And then after that, we'll be discussing about the multiple output converter, which can have about multiple outputs, buck, boost, or combination of both of them. So to start with, why it is called boost converter or a up converter? So it's called the boost converter because the output voltage is higher or larger than the input. Or in other words, we can say that the output is a boosted form of input. So we can start with the basic overview of boost converter. And then after this, we'll be doing the mathematical derivation. So this qualitatively we can easily find out using this circuit of boost converter that this V out, which is the output voltage, is higher than V in, which is the input voltage to this converter. And this controller we know already from our last chapter of buck converter that the output is sensed, fed back to the controller, and based on the algorithm running inside the controller, the pulses for this switch 1 and switch 2 are decided. The pulse frequency or the pulse width is decided based on the algorithm inside it. And this particular current waveform over here, we can see from here that this waveform, the current waveform, is a discontinuous mode of conduction. And in this particular section, we will be discussing both mode of conductions, continuous as well as discontinuous mode of conduction. So during this first phase, phi 1, the controller switches this S1 on. So when this switch turns on or it gets closed, the diode D1 gets reverse biased. Switch S2 we will not be discussing for this basic overview, but we'll see that how this switch S2 gives us a better efficiency. So we'll be using D1 instead in this case. Okay, so when this switch S1 gets closed or turns on, this D1 gets reverse biased and the path of the current is shown by the red arrows over here. So this we know for the input supply voltage is the positive potential, and this is the negative terminal of the input supply, DC supply. So during this phase 1, when this switch is on for this particular time, T on, the current starts to ramp up to this inductor as shown by this part of the waveform till it reaches the maximum value of the current, which is called I peak value of current. And as we can see from the previous section on buck converter, we can easily find out the value of this maximum value of current, which is V in, the input supply voltage, multiplied by the base, which is T on, divided by the total inductance value due to this flow of current. So that will be a maximum value of current I peak. And as we know from the characteristics of the inductor, the energy stored in inductor is half value of inductance L1 multiplied by I peak square, the total current in this inductor. So half Li square. So now in this first phase, the load current through this load RL is supplied by this buffer or filter capacitor C out over here, which was initially charged. So this C out has to be sufficiently large to supply this amount of current in this load RL. So now for phase 2. Phase 2, now switch turns off again or gets opened. And as we know, when this switch turns off, the inductor, after storing its energy, reverses its polarity as per the characteristics of an inductor. So when it reverses its polarity, now these two potentials added together. Okay, so this current will take some time, some finite time. This finite time is required for this inductor current to flow through this diode. So this diode gets forward biased now. And the path followed by the current is shown by the red arrows over here. So this current now charges or start to charge this buffer capacitor over here, which got discharged during phase 1, as we saw in the previous phase 1. So as it was already discharged, so now it starts to charge itself. So now, and a part of this current, which is through this input supply and the inductor, the current starts to flow in this load also. So in this case, this total potential difference, which is a sum of V in plus the voltage stored in this inductor, is now flowing through this load. So we can say from here that the voltage drop in this load is higher in this phase 2 due to the total energy or the total energy transmitted through this load. So now during phase 2, this second phase, the switch S1 gets opened or switched off, and as soon as this switch is turned off, this inductor reverses its polarity, and now the current starts to flow through this diode, which gets forward biased now. But it takes some time, finite time, as per the property of the inductor. And now this flow of current due to the forward bias of this diode D1 starts to flow and charges this buffer capacitor, which got discharged during the first phase, as we saw in the previous slide, to a higher voltage over here, because we know that we have used a higher value of capacitance for this C out from our previous slide. So now this capacitor is stored, or this charge is stored in this C out at a higher value. So now in this, the energy stored in inductor okay. Okay. So now during this second phase, phi 2, switch S1 gets off or gets opened. As soon as this switch S1 switched off, the current through this, or the current through this L1 starts to flow through this D1, which gets forward biased and starts to charge this buffer capacitor, which got discharged during the phase 1, as we saw in previous slide, to a higher value, because we have already seen in the previous slide that this C out is sufficiently large to get charged to a higher voltage. So now this C out, the buffer capacitor, starts to get charged at a higher voltage. And also the energy stored in this inductor is now replaced by the energy stored in this buffer capacitor because of the charging of the capacitor. So now energy is also supplied to the load by this input supply, because we know that as per the positive, this terminals of this supply voltage and the reversing of the polarity of this inductor during the phase 2 both get added up. So a larger value is transmitted, or larger energy is transferred at the load. So for stable situation in the inductor current, it must be able to ramp up and ramp down, as we can see from here, from T on to till total time period, the stored energy has to decrease. It starts to release itself. So the current starts to decay, as we can see from this waveform over here. So in that case, we can say that the output voltage is higher compared to the input voltage. Simply mathematically also we know that the change in inductor current is V in multiply by time turn on time, which is T1, because for simplification we consider T1 equal to T on, divided by the value of L, as we saw in the previous case over here, V in multiply by this one, so that will be the peak current. So starting from here, and when the switch is off, the difference from input and output we'll see, multiply by the time T2 till it starts to release its energy from here, till it releases its energy. That time is called T2. So for that particular time, the voltage in inductor is V in minus V out. Okay, so qualitatively, now this second phase, during this second phase, we know that now the switch S1 gets turned off or gets opened, and during this, when it gets opened, the inductor reverses its polarity, as we already know from the characteristics of inductor. Okay, so during second phase, during phase 2, this switch S1 now is switched off or gets opened. So as soon as it gets opened, the inductor reverses its polarity, as we already know from our previous lectures. So now this current, because this inductor is now energized or it has a stored energy, and this path is now broken. So now this diode D1 gets forward biased. And now this inductor, which has already reversed its polarity, has this point, this node over here is having a voltage, node voltage over here, which is sum of input voltage and a inductor voltage. So this node is at a higher potential compared to the input supply voltage. So now this, if we assume this diode having a very low voltage drop, so this higher voltage over here is appeared at the load over here. So just by looking at this, we can see that as soon as this switch S1 turns off, this current, the inductor current, starts to flow through this diode 1, which gets forward biased. So it gets to flow through this one. And now the load current flows through this load and has a voltage drop, which is equal to V out. That voltage will be equal to this node voltage minus some minor voltage drop over here. So this node voltage is at a higher potential than the input voltage, which is so this node voltage is a summation of the voltage appearing at the inductor plus the voltage at the supply. So just by looking at this, we can say that the output voltage for this particular converter is larger compared to the input voltage. Okay, but we need to find it quantitatively. That will give us the proof of concept. So first, the basic quantitative methodology we'll be using, a simplified version, and then after this we will go for the detailed derivation. So for simplification, T1 over here denotes the turn on time, T on, which we saw in the previous slides in phase 1. And T2 is the time when the switch S1 gets off. So for T1 shows when the switch S1 is on, T2 shows the time duration when switch S2 is off. So during T1, the inductor current ramps up, means it starts to rise. And during T2, when the switch is off, the current ramps down, means the energy starts to release, or the current starts to decay, because when the energy starts to get released, the inductor current will start to decay, as we already saw in previous sections. And we also saw in buck converter the change in or the inductor current, which is equal to the, we can say, voltage multiplied by that time, which is the base T1 divided by L. So this voltage time relationship, we know that the current rising up is equal to the current decaying down, because the net energy in inductor has to be zero. So using that concept, which we saw in previous lectures, that the net energy in inductor is zero, so ramping up of the current must be same as the ramping down of the current, or rising of the current must be same as decaying of the current. So delta I1 must be equal to delta I2. So delta I1 also is the voltage time relation, V in for that particular time t1 divided by L, as we saw in phase 1. And in phase 2, the difference between input and output applied during switch off, which is T2, this is the switch off time, divided by the same inductor value. So both has to be same. The only thing is the direction is negative. So here the current is rising up, here the current is rising down. So the direction is opposite to each other. So here we show by negative sign over here. So if this delta I1 is rising, negative sign shows that delta I2 is decaying. So ramping up of delta I1 and ramping down of delta I2. So equating this equation for delta I1 and delta I2, equating these two together, and we can easily find out that V out is equal to V in divided by 1 minus D, which is the duty cycle. And duty cycle, maximum value of duty cycle can be 100%, which is 1. So in that case, if duty cycle is 1, we can have an infinite value of output voltage. But duty cycle cannot be 1. So just by putting any value over here, V out will always be larger than V in. So proving the concept of boost converter, that output voltage is having a larger value compared to input voltage. So now going further for the detailed overview. So again, simplifying this boost converter, switch S2 is still not used. For practical purposes, we will be discussing about this switch S2. The only thing to understand at the moment is that this switch S2 enhances the efficiency. But in this case, we will be just using diode again. But now for the detailed analysis. So now phase 1 again, when the switch S1 is closed. So this figure B shows when switch S1 is closed or switched on. Diode gets reverse biased, as we already saw in the previous slides. So we have to do it mathematically now. In previous slides, we did it qualitatively. Now we do it mathematically. So what is the value of voltage across inductor? It is LdIL by dt, because this is the current. And we know that the voltage across this inductor, because when this switch is on, this voltage is now connected with this inductor having the closed path, and now the current starts to follow this path, this loop. And we know that the rate of change of current in inductor gives us the voltage across that inductor, which will be equal to the supply voltage over here. So LdIL by dt is equal to VL, which is equal to Vs, assuming no resistive loss over here, assuming a pure inductance. So this voltage will be exactly equal to the voltage in inductor, which is we can show from here. Or DIL by dt, rate of change of current, is Vs by L. Just rearranging this equation over here. And now the rate of change of current we know is constant when this switch is closed. So the change in inductor current is DIL divided by dt. And if we denote it with deltas, having some specific value, because we want to have the change in current for that particular turn on time. So for that particular turn on time of this switch, we need to find out the change in, or the rate of change in, this inductor current. So we can just substitute DIL by dt with the delta IL by delta t. So this delta t is now the total turn on time T on, which can be represented with dt, as we saw in previous lectures. T on time is duty cycle multiplied by the total time period, which is equal to Vs by L from this particular equation. So now we know that this change in inductor current can be written like this when the switch is closed. We can take integral from 0 to dt, the turn on time, T on. So this is the value of voltage or rate of change of current. Vs by L is the rate of change of current and this particular time. So we can, after solving this integral, we get the change in inductor current is equal to Vs by L multiplied by the turn on time. We have already seen it in previous case, but now we are doing it mathematically. This we have already seen. This is the turn on time. This is the input voltage. This is the inductor current. Just by using our electrical circuit theory. Using mathematical analysis, we can find the same thing. Vs is the input voltage, L is the inductor, dt is the turn on time, T on. Okay, so now phase 2, when the switch is opened or when we turn off the switch. Now when we turn off the switch, the inductor current cannot change instantaneously, so it takes some finite time. So during that finite time, the diode gets forward biased. And now with this forward biasing of the diode, as we can see in figure C, this path of this current will now follow this path. And this is the equivalent circuit now when the switch is turned off. So now, what is the value of output voltage over here? And what is the value of the inductor voltage over here? So just for simplification, we can just say that V out can be assumed as a constant value, not varying, no fluctuations, no disturbances. So the voltage across inductor then can be found out by using the difference between input and output, using Kirchhoff's voltage law. So using Kirchhoff's voltage law, we can find out that this inductor voltage VL is equal to the supply voltage or input voltage Vs minus VO, which is the output voltage, which is equal to the LDIL by dt, as we saw in the phase 1. So now again, what is the rate of change of current DIL by dt? It is equal to Vs minus VO by L, or input minus output voltage divided by the inductance value. So now again, assuming the rate of change of inductor current is constant, so the current again is rising linearly or changing linearly, as we saw in the phase 1. So now, change in inductor current for that particular time when the switch is open or off, which is equal to 1 minus dt. dt was the time when switch is on, 1 minus d multiplied by t is the time when switch is off. We have already seen that in previous lectures. So just using the same theory, now we can say that the change in inductor current during this turn of time is equal to Vs minus Vo divided by L, means input minus output divided by L, inductance value. And if we say that now change in inductor current can be represented by this delta IL opened, because this is we are calculating when the time, for that particular time period when the switch is opened. So we can, after solving this integral from 0 to turn off time, for that particular voltage current relation or voltage time relation, Vs minus means input minus output divided by L multiplied by time, which is turn off time, 1 minus D multiplied by T. We can easily find out the value of, then summing both of them together and equating them to 0, because we know that the net inductor current must be 0 or net energy stored must be 0. So this is during the turn on time when the switch is closed, we saw in previous slide, and this is during the turn off time when the switch is open. Voltage time relation, summing both of them up, equating them to 0 due to the net change in inductor current has to be 0. Now, after solving this, we get output voltage is equal to the input voltage divided by 1 minus D, which we saw in previous section for basic overview. So, using complete mathematical analysis, we again found out that this output voltage is larger compared to the input voltage. So this is the ramping up of the inductor current, coil current, and ramping down of that coil current, and so on, repeating itself. So this is a continuous mode of conduction. The current never goes to 0, continuously flowing, ramping up and ramping down. So this is the switch current ramping up, and ramping down is the diode current, because the inductor current ramps up when the switch is on. So this is the switch, the current through switch, and the inductor current ramps down through diode when the diode is forward biased. So superimposing both of these, we get the inductor current, continuous inductor current. Okay, so going further with the mathematical analysis, we know that the power over here, the average power in this particular circuit is output voltage square divided by R, or V multiplied by current, or voltage multiplied by current. So now we can find out input and output powers. We need to equate input and output power just to find out the maximum value or minimum value of the inductor current, as we did for the buck converter, to find out what is the maximum value of the inductor current or minimum value of the inductor current, so that we are able to design a specified value of inductor, so that we decide what value of inductor is required to have this maximum value of current through this in this circuit, or minimum value of current in this circuit. So equating input and output power, so this is the input power, supply voltage, which is the input voltage multiplied by the current, is equal to the output power, which is the DC or the average voltage, which is at the output, divided by the load. So equating these two together, this input power and output power I have already discussed in first lectures. So equating these two together, we get Vs square, which is the input voltage square, divided by 1 minus D square into R. From here, we can easily find out what is the value of inductor current. So IL divided by Vs will get cancelled. We get Vs 1 minus D square. So solving it further, we get output voltage multiplied by output current, which is the load current, divided by the input voltage. We get the inductor current. So now to find out the maximum value of that inductor current, it is IL, which is here, this one, equation 4, from equation 4, plus change in inductor current divided by 2. Because this change in current, we need to find out this average. So that will be the change in inductor current for ramping up, and that will be the change in current for ramping down. So it is broken down into two halves. So that's why we similar case as we saw in buck converter. So delta IL by half. So now adding both of these together, this IL and this delta IL we saw in previous slides, Vs multiplied by dt divided by L, that we saw in the previous case. This one, delta IL closed, Vs divided by L multiplied by dt, equation 1. And equation 2 is for the turn of time, delta IL opened. So from equation 1 we get this delta IL, and from equation 4 we get IL. So adding them both, we get equation 5. That will be the value of I maximum, the maximum coil current or maximum inductor current. Now for minimum value, we need to subtract these two, and we get equation 6. Same as we did in buck converter's case to find out the maximum value of coil current and the minimum value of coil current. Now, we need to find out the boundary between continuous and discontinuous. This we saw for continuous current. Another one is at the boundary of continuous and discontinuous current. And for that, I minimum has to be 0. It touches the 0 line and then immediately shoots up or ramp up. That is called boundary, as we discussed in buck converter's case. So we put this I minimum value equal to 0 and we get this value, Vs multiplied by D divided by 2LF. So that will give us the boundary condition that for that particular value of L or particular value of F, that inductor current will reach 0. So this will help us to calculate the values of inductor and frequency of operation or supply or duty cycle. All these are dependent, all these values, duty cycle, it depends upon our circuit requirement. F, frequency of operation, also depends upon our circuit operation. But L, inductance value, once it is decided, then it will stay in the circuit. So in that case, any of these parameters we can adjust to have a minimum value equal to 0 or minimum value of inductor current equal to 0. That will give us the boundary between continuous and discontinuous current mode. Okay. So now again, based on the previous equation, this previous equation over here, we can easily find out the combination of inductance and switching frequency for continuous current mode, like this one. This L and F, inductance and switching frequency F. So using that, we can easily find out the minimum value of inductance equal to this, just by using the previous equations. Now peak to peak output voltage ripple, as we saw in the buck converter's case, can be calculated from the capacitor current waveform, which is shown here. So the change in capacitor charge, as we already know, can be found out using the output voltage divided by resistance multiply by the turn on time. So during this turn on time. So during this turn on time, this will be the change in capacitor charge, which comes out to be C multiplied by change in output voltage. And this change in output voltage is called ripple, we know that. So that fluctuation in output voltage, we can easily find out using this formula. V naught multiplied by dt divided by R multiplied by C. So using this equation, rearranging this value, putting C, just rearranging this equation, we can easily find out the ripple value over here, voltage ripple over here. And then using that, capacitance value can be calculated based on how much ripple is required for that particular circuit. So once we know that how much ripple voltage is sufficient or is allowed for that particular circuit, we can calculate the value of capacitance. So now we need to go further with the controller design, as we saw in buck converter's case, that how the controller is actually designed to run this boost converter, which decides the switching frequency or when to switch on or switch off these switches. And at the same time, this operation has to be stable. All this is discussed in buck converter's case. So similar concept applies for the boost converter's case.